We're now going to talk about something called power series. This is going to look kind of familiar to the Taylor and Maclaurin polynomials that we've already talked about, but there are a couple differences between a power series and a Taylor polynomial. One, a power series has coefficients that are a sub 0, a sub 1, a sub 2. They form a sequence, which is true also of the Taylor polynomials. But the Taylor polynomial coefficients formed a very particular pattern where the nth coefficient was found by finding the nth derivative, evaluating that at some center value. In this case, we might call it 0. And then dividing that by n factorial. And that was the very particular form that we used for coefficients in Taylor polynomials, or Maclaurin polynomials. For this, these coefficients a0, a1, a2, etc. could be any values. They don't have to follow this particular pattern. So that's one difference. The other difference is that this is a series, so it's not going to stop at an n value. This thing is going to go on forever. So we've spent a long time talking about infinite series in the previous half of this chapter, and a lot of their different properties of whether they converge or diverge. And the only difference between those series and these series is that we have a variable involved. So the behavior of these power series is going to depend not only on the coefficients, but also the value of x that we choose. So you're going to notice that that we have an exactly equals to here. We have an exactly equals to here because we are actually heading off to infinity. And one of the big questions is, what does this infinite series converge to? And another very big question is, for what values of x does this series converge to that value? So that will make a little bit more sense when we look at a few examples. But remember that sometimes we have infinite series that converge and sometimes they diverge, and that's going to depend on the value we pick for the variable x. So when we're talking about power series, we have three different possible scenarios for convergence. Okay, scenario 1 is not a very exciting scenario. Scenario 1 is that the series converges only at c. Okay, and if you think about c, whether c equals 0 in this first example, or c equals any other value in the second example, if you plug in c, then x minus c becomes c minus c. And this becomes 0, and this becomes 0, and this becomes 0. All of these become 0 except for the first term. That first term, a sub 0, is the value that the series converges to at c. So every single power series has that property. So we are guaranteed at least one point of convergence. Okay. Sometimes that's the only point of convergence, but guaranteed at least that one point. Number 2 is kind of the most exciting scenario. The series converges for all values of x. That means it doesn't matter what value of x I pick, I'm going to get a convergent infinite series. And we'll see that from time to time. But the hardest example is scenario 3. That's when we have some sort of finite interval of values of x that the power series converges to. Now, that finite value is called r for the radius of convergence, and it's always centered around c. Remember that c is always a value to which the series is going to converge. And so the idea here is that if we look at a number line and we have our center of convergence here, if we're in scenario 3, then we definitely have this point as a point in our domain, and then we've got some radius of convergence that goes in both directions. So that's going to take us to c minus r over here, and it's going to take us to c plus r over here. And if our radius of convergence is known, then that means that all of these values of x will cause the series to converge, and all of these values of x will cause the series to converge. The only thing left to do is to double check the endpoints. It's possible that the endpoints are convergent. It's possible that the endpoints are divergent. It's actually possible for one to be convergent and the other one to be divergent. So there are lots of different possibilities here. We must check both endpoints in scenario 3. So that's an important thing that you're going to see time and time again on these sorts of problems. And down here, we've got a little bit of a summary of those scenarios. The radius is 0 in part 1, the radius is infinity in part 2, and the radius is r in part 3, and the domain is going to be the interval of convergence between c minus r and c plus r. And again, those endpoints could be included or they could be non-included, and we have to test those. We also, in order to find r, which is the bigger question, we're generally going to use the ratio test. It's kind of nice to have one test that we're going to use each and every time, and that's going to help us figure out what r is. So we remember the ratio test, hopefully. The ratio test gives us that the series converges if we take the limit as n approaches infinity of the a plus first term divided by the a sub n term. If we take the limit of the absolute value of that ratio, if this is less than 1, then the infinite series converges. If it's greater than 1, then the series diverges, but if it's equal to 1, then it's inconclusive. So we're going to see all three of those scenarios popping up in the coming examples.